All right, presenting our next talk is Harriet Drury from Native Instruments. Take it away, Harriet.
Thank you, Josh. Thanks. Yeah, my name's Harriet. I'm sure a lot of you know who I am. I'm a dev at Native Instruments. I'm working mostly on the isotope side. And it's my honor to present our next speaker, Jordan. So I asked Jordan some facts before we started today, because I wanted to make this fun. His favorite band's Flying Lotus, or anything weird or electronic. So if that takes your fancy, go and talk to Jordan about it later. He's from Canada. That's okay. That's cool. Living in, is it East London?
North London.
North London. All right, cool. North London, doing a PhD at Queen Mary. And today we're talking about creating an AI-powered 808 drum synth using JUCE and PyTorch.
Awesome. Thank you, Harriet.
Take it away.
Great. Thanks, everyone. And thank you, Josh, so much for inviting me to be here. Yeah, I've been following the audio programmer for a while, and it's an honor to present and to be here today. So yeah, I'm Jordie. I am a second-year PhD student at Queen Mary University of London in the AI and Music program there, and I'm going to talk about some of my research, which is related to AI and control of drum synthesis and how I made an AI-powered 808 drum synth with JUCE and PyTorch. Before we start, I'd like to acknowledge my supervisors, two academic supervisors, Professor Andrew McPherson at Imperial College London, Dr. Hara Lampo-Saitis at Queen Mary University of London, and my industry supervisor, Dr. Andrew Robertson at Ableton. Very grateful for all of their mentorship. They have contributed a lot to the ideas and this work. So, what is my PhD thesis? Just to give a little bit of context, I'm looking at real-time control of audio synthesis, and my goal is to get rid of the keyboard. Not actually, I actually really like keyboards, but I am working on this audio-driven synthesis topic. I want to use acoustic instruments to control audio synthesis, particularly percussion instruments, looking at how can we use skills that musicians already have on their acoustic instruments and take advantage of the richness of audio signals, extract information from these audio signals and map them onto controls for synthesizers, potentially giving novel ways for musicians to explore the space of possible sounds here and just be creative in new ways. In particular, I've been quite interested in this topic of differentiable digital signal processing. This came out of a paper from the Google Magenta Lab a few years ago, led by Jesse Engel. And the idea here is to be able to take this rich history of DSP algorithms and research in that field for audio synthesis and audio effects and put that together with neural networks. So instead of just having neural networks replace DSP altogether, is actually how can we combine these? How can we use neural nets to control DSP? And so I'll give an example of this DDSP harmonic synthesizer. This is the synthesizer from that paper implemented inside of the Newtone plugin. And this is an example of a flugelhorn being timbre transformed into a Japanese flute called the shakuhachi. So we'll start with the flugelhorn. Yeah, so when I first saw that, I thought that was pretty cool. And I really like this idea of integrating DSP. So there's a harmonic synthesizer under the hood there. But I'll quickly go over all the ingredients of a DDSP synthesizer and how these all come together. So the first is we have some input. This is probably audio, maybe some audio features we've extracted from a live instrument, like pitch, loudness, some timbre features, or maybe it's just MIDI. In the case of that DDSP synthesizer, it's pitch and loudness. Then we have a neural network, which we train it, it estimates DSP parameters from input features to control the DSP synth. And then this is the DDSP part, so we have some DSP function, harmonic synthesizer, filtered noise in the case of that synth I just showed, and these need to be differentiable. And fortunately, what this really practically means is that we write them using an auto-differentiation package like TensorFlow or PyTorch, and we express these functions using the math API of those libraries, and then those libraries take care of the challenging part of calculating derivatives and passing gradients through. So it's not too challenging. And then, so this receives parameters and generates audio. And then finally, we have some measure of loss. In machine learning, we have a loss function, and this computes how wrong we were when we make an estimate. And the cool thing about DDSP is we can calculate this directly on audio, so it's closer to perception in a sense. So in the case of this DDSP harmonic synthesizer, we have our training data, maybe it's a violin sound or that flute, and we want to match it perfectly at the output. And we use a spectral loss, so we compare those functions, that audio in the frequency domain, and we get a sense of how wrong we were. And so we get this measurement, and then we're able to backpropagate through our differentiable functions and update our neural network to hopefully make a better guess next time. And so the question that I'm looking at is, what about drums? Can I use drums for this, and what if I want to use a different synthesizer? So if I have an acoustic drum at an input, well, pitch doesn't really make sense. It's like, yes, you can have tuned drums, but pitch extraction in real time doesn't totally make sense. Harmonic synthesis doesn't really make sense also for drums. And then if I'm using something like an 808, does it really make sense to try to match perfectly an acoustic drum with an 808? Probably not, but I still would like to control this somehow. Can I still use this technique? And so I've been exploring this idea of timbre remapping. It's not my idea. It came from Dan Stowell in 2010 from his PhD topic. And this idea really is, for real-time timbre remapping, we want to extract audio features from a live input instrument and map those onto a synthesizer parameters, so timbre expression from the input instrument performance is translated onto that synth. So we want to take this sense of an expression through timbre and map that onto synthesis parameters. And so this is an overview of the system that I've built for percussion. So we have input audio. We detect features from that input audio in real time at detected onset. So we have percussion, so we have a sense of there being something happens, we detect features, we pass this to a neural network, and then this estimates parameter updates for our 808 synth in real time. And then we have this offline training portion of it where we extract features from this, and we came up with this thing called the feature difference loss, which I'm going to explain more, and this gives us the ability to map from timbre spaces, one of an acoustic drum synth and the timbre of an 808. And really what we're trying to do here is, instead of perfectly match the output with the input, is to match the shape of the sound. How are these features evolving over time? How does loudness evolve over time? How does timbre evolve over time? And match these contours. And so this comes from an idea of a timbre analogy. And so just to give a little bit of a background on what a timbre analogy is, this is based on some timbre perception research. And so this concept of timbre analogy, really it says, if you can imagine that the orange dots down at the bottom, A and B, are two snare drum hits on the same drum, and they vary by some amount. And then dot C up at the top is a synth sound. And so we want to try to find sound D, so it varies in the same way that A varies from B. So we have this analogous variation with respect to some timbre space. So we can plot this. So I can take a snare drum performance and start to plot these variations in a timbre. I'm calling it a timbre space. The y-axis is loudness, and the bottom is spectral centroid, which refers to kind of like brightness. All right, so now we have this sense of there being variation. We have a little bit of data set that describes the variation of this musical phrase. And then now we want to introduce a synthesizer. So we have a synthesizer. We start with a preset, and we can also plot that preset sound in our timbre space. And then what we want to do is basically learn modulations so that we stretch that preset sound to match those same variations with respect to loudness and spectral centroid and whatever other features that we have. And so this is the concept that I've used to develop a plugin, and so I'll give you an example of what that sounds like. So this is my friend Carson playing drums. It's going to be the acoustic bit, and then followed by the 808 timbre transferred bit. Yeah, and so those were all generated in real time. And I've also, so this is what the plugin is looking like. And And so we have some controls for onsets, displaying the input features, and then controls for synthesizer, just like you'd expect. And I've been having a lot of fun just passing in random drum loops to it. So here's an example of that. So now this is fully just the 808. And so kind of like mixing in with a dance track. And so I've been having a lot of fun messing with that. So now I'll go through basically how I designed this and implementing this in a plugin, starting with this differentiable 808 synth. So the design of the 808 is based on this practical snare drum synthesis article by Gordon Reed. This whole series is absolutely phenomenal. It's really just like it's an inspiration of an 808. It doesn't do any of the analog circuit modeling. But it's pretty simple. There's two sinusoidal oscillators. Each of them have exponentially decaying frequency and amplitude. Then there's a noise generator also with exponentially decaying amplitude that passes into a high-pass filter. Those are mixed together and then pass through a wave shaping function. And so in total, there's 14 parameters for controlling this synth. And so how do we write this differentiably? How do we make a differentiable 808? And so fortunately, with stuff like with PyTorch, it's relatively straightforward.
Just explain differentiable.
Yeah, absolutely. So differentiable refers to functions. A function is differentiable. I'm not a mathematician, but it is, if it's a continuous function, it doesn't have any breaks in it, we can calculate the derivative of that function, and then we can use that to basically compute the gradient of a function in a machine learning environment. I don't know if that's helpful or not.
Sort of, yeah, getting there.
Yeah.
So when you say differentiable 808, you mean what?
So what I mean by that is that I have a function that is, it's my synthesis function,
Yep.
and then I can differentiate that whole function with respect to the parameters. Yeah. Mm-hmm. Yeah, I'll share some articles at the end that really break this down. David Trevelyan gave a talk at ADC a couple years ago and really step by step through what it means for something to be differentiable, and what does this mean with respect to like machine learning. And I don't have time to go through all of it. I probably would butcher it too. But yeah, I'll pass that along afterwards. So I'll practically show what this looks like to write the 808 synth. Starting with just a basic synth module. And so I'm going to write this wave shaper tanh function. And so this is a synth module class. And so in the constructor, we have the required parameters. So there's just an input gain. This is just a parameter normalizer, and so it allows us to convert from 0 to 1 to this human readable range. Decibels, the range is -24 to 24. And then the DSP function call with audio and parameters lives here in this forward pass. And so this is called when we're making, just basically using the synth as we would, passing forward. And then PyTorch knows how to calculate the derivative of this automatically because we're using torch tensors, importantly, as the input. So X is audio coming in, and then we have input gain, which is the parameter. And then all of the math functions we're applying either directly to tensors, or we're using these functions, this torch pow and torch tanh. And so just to give a little background, tensors are just multi-dimensional arrays, but they have support also for running on GPUs and support this automatic differentiation. And so it's a little bit different than writing regular DSP code. Everything happens with matrices. And so when we call this synth, it generates a full scale, like second of audio, 2 seconds of audio, all in one chunk, as opposed to having for loops iterating over blocks. So it's a little bit of a different way of thinking, or generating using these like matrices as opposed to for loops and stuff. And so now we have this full synthesizer. This is a snare 808, also implements this torch NN module, and then all of these synth module blocks are just become class attributes here. And then in the forward call, I'm not going to go fully through it, but all of the parameters are passed as a tensor, and then we just go through and basically call all the individual functions, the synth modules, to generate the 808 sound. And then this is what it looks like running the synth. So I have here this constructor for the snare 808 sound, initialize it with a sample rate, which is 48 kilohertz, and then I'm telling it that every time I say, give me a new sound, it's going to generate half a second of audio here. and then I'm just generating 10 random presets. So this is just a matrix of randomly sampled values. So it's 10 by the number of parameters, which is 14, and then it's generating that many parameters when I call this forward pass call. And so this is what 10 random these 808 sounds sound like. So not very snarey. It's just sort of like random signs, but it can make a snare drum sound. It is a snare drum, but kind of happens what you would expect if you just randomly generate it. We don't need to listen to those again. Okay, so I'm going to talk through what this feature difference loss is, and go through this. And so this is what allows us to do this timbre remapping. And so we'll start with a snare drum hit. We pick one hit from a musical phrase, and then we have a corresponding synth preset, which I've pre-programmed. And then define a set of feature extractors. So I selected some from previous literature that was looking at snare drum performances and timbre. And so these features include loudness, spectral centroid, which is a measure for perceptual brightness, or it corresponds to brightness, spectral flatness, which measures the noisiness of a signal, and then temporal centroid, which is the evolution of an amplitude envelope. So basically, you can measure if a snare drum is really snappy and really quick with decay, then you'll have a low temporal centroid. If it has a long decay, then it'll have a longer temporal centroid. And so then we compute these feature differences. So starting with the snare drum on the left-hand side there, we have the anchor sound, which is XA, and then some varied sound, which is XB, and computing the difference between those two, and this gives us a sense of how much these two snare drums hits in a phrase have changed. And then similarly, doing this for a synthesizer. So there's the preset, and generating the sound that corresponds to that preset and the features, and then modulating that, and generating that sound, and then computing the difference. So looking at how much does this synthesizer sound change when I apply this modulation to a preset. And then so the goal here is to learn parameter modulation. So the feature difference between the synthesizer preset and the modulated sound is equivalent to the difference between the input snare drums. So to do this, we compare the difference between feature differences using an L1 loss, or the mean absolute error, and call this whole formulation just the feature difference loss. So now with this formulation, I haven't introduced the neural net yet, but with this we can individually learn parameter modulations. And so we can see what that sounds like. I'll play the snare drum first and then the modulated synth. It's a little bit quiet. There we go. Okay, great. So now let's look at this whole system as a whole and figure out how do we do this in real time. So the goal is to create a real-time performance system, and so we want to be able to estimate these timbre analogies, these synth modulations, in less than 10 milliseconds following a detected drum sound at an input. So our proposed system uses onset detection to detect incoming drum hits, and then audio feature extraction, but now audio feature extraction at a very small window of sound. We're pulling out 256 samples, which is less than 10 milliseconds, and then computing features on those, or computing loudness, spectral centroid, spectral flatness, and then these are passed into the neural network, which then predicts the synth parameter modulations. And so now going back to this real-time timbre remapping, with this feature difference loss, we insert the onset feature extractor, which is on the varied snare drum. And then these onset features are then passed into the neural network. And so just to point out that the onset features, that FO, those operate on that small window, whereas all the other features have access to the full drum sound. So they can see the whole drum sound during training, and we're computing that and computing the loss based on the full drum sound. And so this is during training, and then during inference, we can pull that all out, and we just have the onset detector with the onset features and our trained neural network, which is estimating modulations. And so this now brings us into the plugin. So this is the part that sits into a plugin here. And so what I've done is re-implemented the onset detection and feature extraction in C++, along with the differentiable synth, which is no longer needs to be differentiable. I'm just writing it as a plain C++ synthesizer. and then using libtorch, so the C++ backend for PyTorch, and using this to actually run inference on the pre-trained model. And so this is fast enough to run on the audio thread. It runs in less than a millisecond, so it's quite fast. And then the model itself is exported from PyTorch after training into a Torch script model, along with the preset that was used during training as well. And so, I'll quickly talk about a little bit of the C++ code. Using the torch.script library is not too difficult. So there's a dedicated library, C++ library for loading modules and doing everything you would want to do in PyTorch. So it's really just one line there, that torch jit load path. And this is really nice because then we can have the models actually act as presets. So each pre-trained model then becomes a preset that you can load from the user interface, and then it's loaded on the fly there. And then running prediction with the model down below there is also relatively straightforward. The bottom line, which you probably can't see from the back, but it just says model forward and then convert the outputs to a tensor. And there's a little bit of data massaging to get the input features into the correct format, but it's really, it's not too challenging. And then with the UA design, I just wanted to give a quick acknowledgement to Louis Wolstenholme and his bandmate Francis Devine from Julia Set. They did a really awesome job on this. And so, I just wanted to quickly shout that out. And I've got this nice black square at the bottom there. It's engineering notes, a couple things along the way. So compiling with the JUCE support for CMake is really brilliant. Makes it really easy to include libtorch with just a few lines, find package, set the CMake flags, and then link the library. Building I found to be a little bit more challenging. libtorch has a lot of hardware dependencies, hardware-specific dependencies, so I found most success with actually installing Torch using Python. And then they have this utility function which provides a location for the CMake prefix path for libtorch. And then, so I store that as an environment variable and then pass that into the build, which seems to work much more reliably for me. Another thing, so testing C++ and Python. Jan Vilcek gave a really interesting talk at ADC last year on how to combine Python testing with C++, so testing C++ code from Python. So this was really great because a lot of my synthesis code is started off in Python and then navigated to C++. And so what this looked like is compiling the plugin, the plugin DSP code in a shared library and then loading that in Python using CPPYY, and allowed me to compare Python implementations with C++ implementations, which is super useful. So just to kind of like conclude, I have a few more slides here. I wanted to also talk about some of the challenges with DDSP. It's really fun. I really enjoy writing these synths and experimenting with them. There are definitely challenges along with it. Certain important parameters are hard to estimate using DDSP. Frequency and pitch parameters, FM modulator frequencies are notoriously difficult to optimize. And this is demonstrated by this plot here. This is a spectral loss. So you can see this is the true frequency down at 100 hertz. And this is what the loss surface looks like as you have a sine wave and you're trying to find the frequency for that. And so if your sinusoidal oscillator had its frequency initialized at something like 300 hertz, your optimizer is going to have a really hard time. Like it's just like there's so many local minima along the way. It's not a smooth surface, and so this is a really hard problem. Fortunately, there's some really smart people out there working on this. Some people at Queen Mary University working on this right now, Ben Hayes, and making some good progress on it. But it definitely has limited some of the applicability for this work, and there's definitely challenges that cropped up in this work as well. And then, of course, there's the engineering overhead of just having to write in Python and then convert to C++. So here's some DDSP resources that if you're interested in digging more into this, there's some really great stuff in there. There was 2 ADC talks there. There was a talk by the original Google, well, not the original, but someone Google people from Google Magenta who looked at implementing DDSP into a VST, and then, like I mentioned, David Trevelyan's talk, which gets into more of the nitty-gritty of what it means for a function to be differentiable and how that integrates into machine learning research. As well as a couple of my own resources, or resources that I collaborated on, a DDSP review paper that I was co-author with Ben Hayes. And then last year at Izmir, the Music Information Retrieval Conference, we did a workshop on DDSP for audio synthesis. And again, there's some good resources there if you're interested in wanting to get going with this kind of stuff. That's all on Python, and a lot of the building blocks are there. Yeah, thank you. So this is going to be part of a NIME paper. NIME is next week, the Conference for New Interfaces for Musical Expression, and I'll be sharing the plugin next week there. So thank you so much.
All right, I'm sure there's like a million questions. Thank you for that.
Thank you so much.
I wonder if I can ask the first question.
Yeah, absolutely. Yeah.
What does your PyTorch model look like, or is that a secret?
The PyTorch model.
Yeah,
oh, it's not a secret at all. It's really quite simple. It's like a MLP model. I think there's like 3 layers.
That's nice. Nice
yeah,
and simple.
it's quite small. It has less than 6,000 parameters. So it's like, because it's such a dedicated task, and this is one of the things that's really nice with DDSP, is because you have like a very constrained task. You can use small data. There's like train models with like 2 minutes of data. It takes 15 minutes on a CPU to train.
Nice.
Yeah.
Nice. So you've got like super quick iterations of this. You can just keep
totally.
going session. Next question is, have you tried this in like a live situation, or have you just got like one mic on a snare at a time? Have you like tried to filter anything? Have you done that before, or is that like to come?
Yeah, I definitely want to be working more with drummers in live situations, so if there's any drummers here and want to play with this, hit me up. But no, it's definitely been in like very constrained environments. Like I did the session with my friend Carson Gant, One Up Drum Vid. We were just playing with this snare. And kind of like this kind of environment. Definitely like one of the things that he brought out to talk about is like it relies on onset detection, and so that requires a little bit of tuning and will trigger with other drums as well.
That was my thought.
Yeah.
Like, that was my first, like, how do you get this to work so specifically? But I mean, problems for the future, right?
Exactly,
so,
yeah.
Lovely.
I still got 2 years.
Yeah. All right, any more questions? I'll go over here to Garen.
Hi.
Hey.
Great talk, thanks.
Hey, thank you so much. Yeah.
So the features that you extract from the performance, you have chosen things like the loudness and the centroids and so on.
I have.
How is the model sensitive to exactly how those are phrased, and is there a way to find which ones are good? I noticed that in the snare performance there was I don't know the terms, but the main bit, the snare, and then the rim.
Mm-hmm.
And are there other detectors that might be better at, like, you know, can you learn which things you're analyzing as well as how you use them?
Mm-hmm. Yeah, that's a really good question. This is a hard one too. This like, this feature representation or representing audio. I selected those particular features from looking at literature that talked about timbre variation in snare drum performances, as well as talking to a drummer who, Rodrigo Constanzo, has done a lot of really great work with ML and drums as well, and he's landed on some of these features, and so I kind of just used that as a starting point. But there's a lot more exploration to do there, and then also there is some work in learning that as well. There was someone from our lab, Andrea Martelloni, did some work on actually learning features for percussive, it was like percussive finger style on an acoustic guitar. And so that's something that you could definitely look at as well, yeah.
All right, any more?
Thank you.
Over here.
Hey, I've got actually a sneaky couple of questions. So one is, obviously, there's loads of different ways to do like resynthesis and that, and you could, in the old school way, use like envelope followers and stuff. So, what are the benefits of using machine learning instead of other approaches like that? And the other thing was not directly related to the content of your talk, but it made me think when you were talking about noise and stuff. Are the techniques of stable diffusion applicable to audio as well?
Mm-hmm. So I'm definitely not, starting with the second one, I'm not a diffusion expert, but diffusion is being used for audio synthesis.
Okay.
As far as I know, it's not applicable to real time right now. Like, I don't think you could have something controlling it in real time, as far as I know. But I think in terms of like fidelity and quality, I think diffusion is the best if you have the time and compute to wait for rendering.
Right.
And then for the first question in terms of synthesis methods, yeah. So I mean, you certainly, and the benefits of using machine learning for something like this. So this project actually started off without any machine learning as a course project last year, where I was working with like a little Bella board, and I implemented like an 808 style synth on it for a class project, and then just was mapping features directly to the synth parameters and creating those mappings myself. And so where the machine learning part of it comes in is like, well, could I infer those mappings? Could I learn those mappings automatically from a recording? Could I have someone be playing on a drum and then learn directly those mappings? And that's kind of where this process comes from. Is so
So it automates parts, so it's kind of knobless, so to speak.
Yeah, exactly. It's sort of like, now I have this non-linear mapping that's been learned, and I can kind of like drop them in and experiment with them.
Great. Thank you very much.
Yeah, thanks for the question.
Any more from this side? I'll take one more from this side and go over.
Hey, hi, great talk. I'm Sasha. I know some of your supervisors. So.
Nice. Great.
Yeah, great work. One question. I didn't quite get how you trigger the note on the synthesizer side. I'll tell you, once you tell me the answer, I'll tell you what I have in the back of my mind about this question.
Like the onset detector?
Yeah, you have an onset detector.
I have an onset detector.
All right, okay.
Yeah.
Because so the model is specific to the 808 synthesizer, right? If I were a musician, what I would want to do is do my drum set and then be able to change the type of backend that I have to render my drums.
Yeah.
And the natural way to doing that is having a MIDI transcriber, right? So if you had, have you tried that, or maybe it's an idea for future experiments, if you had a dual stream in your neural network, like if you were adding the MIDI parameters to your timbral representation, would you achieve a better MIDI transcriber than something that has no knowledge of the rendering of the drums at the end of the pipeline?
That's a good question. I don't have an answer to whether that. So the question is whether that would improve automatic transcription if you had this information.
Presumably both, because if you have something that the more information you put in your learning, the more sort of constrained the optimization becomes, the better your results. In principle, I don't know, it might fail miserably, but so in that sense, you would have a sort of effectively dual head thing, one which transforms the drums into the natural drum into the synth parameter, but another one which provides a MIDI transcription. So if you condition one on the other, would that help the MIDI transcription because it's got a better knowledge of the timbre?
Probably. I think that would be a really interesting experiment, and I think there's been, not for transcription, but it makes me think of some interesting work in like source separation that used a DDSP modeling type approach where they were like resynthesizing a mixture, but in the process, modeling the instruments along the way, and then that resulted in this, like at the end of the day, this source separation technique. So it's sort of like this resynthesis task, but also helping you with a middle task like transcription, in this case source separation. So I think it would be an interesting experiment for sure.
Cool. Something to have fun with. Thank you.
Yeah, absolutely. Thanks for the question.
Thanks. I also have a sneaky two questions. The first is, you mentioned that there's like a sort of exponential decay component, and that's a parameter of the synthesizer. I was wondering if after the onset detection, once the synth is triggered, whether the model actually ever ends up modulating that decay parameter after that sort of trigger?
No. Okay. That's something I would like to do, but right now what it does is it just at the onset calculates the features, figures out the parameters, then triggers the drum, and that's kind of it.
But is there a technical reason why that happens, or it's just because when you hit a drum, the envelope doesn't naturally change after you've hit it?
It's more that it was easier to do it that way. There's certainly, like updating this so you update the synth as time goes on after the onset would certainly be interesting, because I mean, you can interact with the drum afterwards. It's like, there's the simple case of hitting a drum and it decays, but you could like damp it. That would be super cool to be able to model that kind of thing.
So you're saying the model actually doesn't change the parameters after the onset?
No.
In kind of real time? Okay,
But
interesting.
if you hit the rim, you get a short sound, and you hit the drum in the middle, you're getting a long sound, so it's inferring that from the onset.
Exactly. Yeah, you got it. Yeah.
And then another, quick question. Like you also mentioned that you had like a sort of, you had to make a training data set by getting samples of drumming and then manually creating synth presets. Is that correct?
That's correct.
Yeah, so I was just curious, like how many did you have to do by hand to be able to train this?
So actually, one model corresponds to a single training, so like a minute or two of someone playing a drum and a single preset.
Okay.
And since the models, so yeah, you have like a model and a preset pair, and that kind of becomes its own little preset, but it's a new model for every single preset, if that makes sense.
No, but I mean like for training a particular model, did you have to?
Just one
Okay,
preset, a single
okay.
preset and a short recording of a drummer.
Okay, I see.
Yeah.
All right, thank you.
Yeah, so it's a little bit of a different thing. Instead of having one big model, it's many small models. Yeah.
Okay, any more questions? No, I think we're fresh out. Any more this side? No. Okay, well, thank you.
Awesome. Yeah,
That was
thank
a
you.
great
Thanks,
talk.
everyone.
Thanks, guys.